Chris Hawk. I'm representing the red team, and I'm going to talk today about the filtered wash pump control system. An outline of what will be covered, basic system information, the steady-state operation of the system, analysis of the transient flow through both visual and FOPDT analysis, a side-by-side comparison of the results from the two, and the conclusions. The background on the system is modeled after a system in a sewage treatment plant here in Chattanooga. Filter is used to separate out sewage sludge to be taken to a landfill, and wash water is used to clean the filter. A variable speed pump, the P305, drives the water towards the filter washing nozzles and the two manual washing stations. The two manual washing stations are for spill cleanup and things like that, but for our analysis, both of the valves will be closed and we'll only be concerned with the filter washing nozzles. The FT301 is the flow rate transmitter, and the pump speed comes from FRC 301. The input for our system is the electrical power of the pump, and the output is the flow rate of the water in pounds per minute. The objectives of our analysis is to develop a steady-state operating curve, observe the system's response to a step function, find the gain, time constant, and dead time for the system, and find both of those parameters through both visual and FOPDT analysis. This is an example of a steady-state input. The blue line is the input for the system, and the red line is the output. The steady-state region occurs after the initial startup of the system when the output stabilizes. This is the steady-state operating curve that we have developed for our system. The operational output range is between 20 and 38 pounds per minute, and the corresponding operational input range is between 65% and 98% power to the pump. For the simulation of transient flow, our inputs are the input baseline, which is the initial pump power, the input step, which is the change in pump power, the time of the step, and the duration of the experiment. And during the step response, the output will rise by a certain amount, and the output will also lag for a certain period of time after the step and the input. This is an example of finding the values visually. It's a 65% input base with a 10% step. It occurs at 10 seconds. Delta M is the change in the input. Delta C is the change between the two steady-state output regions. The dead time has to be estimated in order to find the time constant. You take 63.2% of the change in output, find the point in time at which that occurs, subtract from that the time at which the input step occurs, and then subtract the dead time and you find the time constant. The gain is the change in output over the change in input. In the FOPDT modeling, this is the equation that we use. C of T is the output of the system, A is the input step, TD is the time of the input step, TO is the dead time, and K is the gain. Tau is the time constant. For our analysis, the A and TD are known, so we will adjust the dead time, gain, and time constant in order to make it a best fit for our data. This is a FOPDT analysis of the step-up model. As you can see, the model output is overlaid over the data output, and you adjust the gain, dead time, and time constant to make it a best fit for this. This is an FOPDT step-down model. It's done the exact same way, except for the input step is negative. Just adjust the values and get the best fit. This is a side-by-side comparison of our analysis results for the gain. The visual analysis is the orange bars, and the FOPDT analysis is the blue bars. We did this on three different ranges. We did step up and step down for each range, and we did 3 tests per step up, step down for each range. So it's a total of 18 experiments. This is the comparison between the FOPDT dead time and the visual dead time. same thing. And here is the comparison between our time constants for the visual and FOPDT analysis. The conclusions, the input range was from 65 to 98%. The output range was between 20 and 38 pounds per minute. And the FOPDT system parameters that we found, the gain was 0.48 pounds per minute per percent. The dead time was 0.44 seconds, and the time constant was 0.8 seconds.